Okay, the last thing I wanted to do in Chapter 5 is I wanted to look at some applications of exponents and logarithms. Exponential growth and decay is a major application, and so I had attached a worksheet here with a bunch of problems on it, and the idea was just to have you guys kind of look at these, although I was going to do some of these together with you right now. So before we look at a couple of problems, in a lot of the problems we'll be using the function which is written here, p of t equals p sub 0 times e to the kt. This is a function that models how many types of populations grow or get smaller over time. Whether that be the population of people or the population of bacteria or the population of money, or usually when you're studying how a population is growing over time or getting smaller over time, it's going to be something that either looks like this formula or very much resembles this formula somehow. Okay. P sub 0 is the population at time 0, or it'd be the initial population that is there. P is the population at time t. T is the time. K is sometimes called the exponential rate. Okay, now if K is positive, that means that you're going to have exponential growth, so the population is going to be growing over time. And if K is a negative, that means you'll have exponential decay, and so therefore the population is going to be getting smaller over time. So we're going to know in these problems if the population is growing over time or getting smaller over time just simply by identifying that K value, whether that's a positive or a negative. All right, so let's take a look at a couple of these problems like I said here. Problem 1 on this sheet says plutonium-241 decays according to the function a of t, which is given there, where a sub 0 is the initial amount present and a is the amount present at time t, which is in years. Assume that there is an initial amount of 500 grams of plutonium-241 in the sample. Okay, so here's my function then that I'll be using. I've got initially 500 grams of plutonium-241 in this sample. That'd be the value of a sub 0. And notice how in this problem we're going to be working with exponential decay. All right, the exponent is a negative, so over time there's going to be less and less plutonium in the sample. All right, now in part A, it says how much plutonium is left after 4 years. And then part B, how much is left after 8 years. Part C, how much is left after 20 years. Okay, let's take a look at those three first. So if I want to know how much is left after 4 years, all I do is just simply plug 4 into the function that is there, and then go to the calculator. Okay, so you've got 500 times e to the power negative 0.053 times 4. Okay, and then I'm going to hit enter, and I'm getting 404.48. If you go nearest 2 digits, I'm going only 1 digit there, that's fine. Grams, that's how much would be left after 4 years. Okay, and then part B, you'll plug in 8. So, if I have this retyped again, I just let T be 8. And here's that next number, and then if I plug in 20, here would be that number then for part C. So those are the numbers that I'm getting from my calculator, you can see, and of course there's rounding on all three of those. But you can see over time here how there's going to be less and less plutonium-251 in the sample, 241 in the sample. Okay, now part D of this says what is the half-life of plutonium-241? What they mean in that is how long are we going to have to wait until we get down to half of what we started off with. Like we started off with 500 grams of this, and you can see how it's decaying over time. Like how long are we going to have to wait until we get down to 250 grams? A is the amount, so I would just simply set the amount equal to 250 and solve for t. Before I solve this equation, notice how, just an observation here, 250 is between 173.2 and 327.2. So I should expect to get a time that is between 8 years and 20 years. Okay, and I'll check that at the end here, but yeah, so I've got to solve this equation for t. Divide by 500, 250 over 500 is 1/2. The bases are not going to match nicely for me here. Like there's no easy way to rewrite 1/2 as e to some power. There's also no easy way to rewrite e as 1/2 to some power. Okay, so I'd want to consider using logarithms next. Take the ln of both sides. That allows the power in front of the logarithm there to the power inside the logarithm to come in front of the logarithm on the right. And so on the right, I'm looking at negative 0.053 times t times the ln of e. Remember that the ln of e is 1. And now divide both sides by negative 0.053. Okay, if you go to the calculator then and type in ln of 1/2 divided by negative 0.053, I'm getting 13.08. We go nearest 2 digits on that. Okay, and the time is in years, so a little bit more than 13 years. And by the way, that sounds right? We expected there to be between 8 years and 20 years, and so in fact this number is right. But that would be the half-life then of this. Okay. Let's take a look at problem 7. It's another one. So in problem 7, it says, how long does it take any quantity of iodine 131 to decay to 25% of its initial amount, knowing that it decays according to the function a of t, where t is the time in days. Okay. A sub 0 is the initial amount of iodine in the sample. Now, they're not giving us a number like they were giving us a number in the last problem. That's okay. Whatever the amount of iodine is in the sample, I want to know how long it's going to take to get down to 25% of that original amount. 0.25 times A sub 0 would be 25% of the original amount. And so that's the expression that I'll want on the left side of this equation. And now I'm all set up to solve for t. If you divide both sides by a sub 0, by the way, a sub 0 is not 0, okay, because, for this problem you would assume that there's at least some quantity of iodine in front of you. Okay, like it's not a trick question, like you got nothing in front of you. Okay, so whatever that quantity is, whatever that positive number is, you're going to divide by that number, and here's our next line. Okay, notice how the bases are not going to match up nicely, so I want to take the ln of both sides. That will allow me to pull the power in front of the logarithm on the right. So on the right, I'm going to have negative 0.087 t times the ln of e. The ln of e is 1. And now divide by negative 0.087, so that t is all alone. If you go to the calculator and type in ln of 0.25 divided by negative 0.087, I was getting roughly 15.93 days, if you go nearest 2 digits on that. The time is in days, by the way. So yeah, a little bit less than 16 days is how long somebody would have to wait to get down to 25% of whatever the amount is that they originally started off with. Okay, let's try problem 9. There's another one here. Problem 9 has a couple of different parts related to carbon-14. We're just going to do part A. Parts B, C, and D are going to be very similar to what you see I'll be doing here in part A. Says carbon-14, which is also known as radiocarbon, is a radioactive form of carbon that is found in all living plants and animals. After a plant or animal dies, the radiocarbon disintegrates, and scientists can determine the age of the remains by comparing the amount of radiocarbon with the amount present in living plants and animals. This technique of comparison is called carbon dating. The amount of carbon-14 in a specimen after T years is given by the function y, which is a function of time t. Y sub 0 is the initial amount of carbon present in the plant or animal, whatever died a long time ago, at time 0. So part A, it says a sample from the refuge deposit near the Strait of Magellan is found to contain 60% of the carbon-14 that it originally had. What is the age of the sample? Okay, so here's the equation that was given to me. Y sub 0 is the initial amount of carbon-14 that is in this plant or animal, whatever died a long time ago. We know that there is 60% of the original amount that is left. Okay, so 0.6 times y sub 0, which you see on the left, that would be representing the fact that there is 60% of the original amount still there. So here'd be my setup equation. Notice that, again, I've got exponential decay going on, right? After the plant or animal dies, the radiocarbon disintegrates. Whatever that initial amount of radiocarbon was, well, again, we're not given a number, but you're going to divide by that number, y sub 0. Y sub 0 is not 0, by the way, since we were told in the summary that I read that every plant and animal has at least some radiocarbon in it. Okay, so whatever that positive number is, you're going to divide by that number there to get the next line. The bases are not going to match up nicely for us, so we'll want to take the ln of both sides. That will allow us to bring the power in front of the logarithm on the right. So you're going to have negative 0.0001216t times the ln of e. The ln of e is 1. Divide both sides here by negative 0.001216, and that way t is all alone. You can go to the calculator then and punch this in. And I was getting roughly 4,201 years old if you rounded the nearest whole number value there. Okay, so pretty old, this thing that was found there. I'll do a couple more problems on the next video.